and store called as single register load store instructions, and we have multiple register load store instructions. So we have clearly mentioned a single register load store instructions started with LDR, okay, load register LDR, okay, and then STR, store the register onto the memory. Load the register from the memory, store the register onto the memory. So that is what the single register is all about. Single register has a byte concept, word concept, half word concept. So it means LDR with byte, okay? I mean load register with byte, load register with word, load register with half word. Likewise, simple analysis with respect to registers and the memory. So single register instructions, single register load store instructions will occupy less number of cycles. It means they need very less number of cycles for the execution, and the load and store instruction single register concerned will not be efficient when it is compared to multiple register instructions. So whenever we want to access multiple locations of the memory simultaneously with the single instruction, so multiple register load store instructions provide such instructions. A single instruction will allow us to fetch the many memory location contents onto the register or from registers onto the memory. So what are such examples if you list? LDM, STM. There it is R, it is M. So LDM, STM. LDM, load store multiple instruction, okay, with addressing modes associated. There are 4 different addressing modes I specified in the last class. That is what the list here. And how the instruction looks like: LDM/STM with addressing mode RN, okay. RN is the base register along with what are the registers, the range of registers which are associated, okay. So that is one thing. So next we have said with that this location, this is what the example we discussed. You can see here this is not getting enlarged, okay. So in this, what is that we have seen is what is that we can say here is what are the different load and store instructions. I mean multiple instructions available: LDMIA, LDMIB, LDMDA, LDMDB, STMIA, STMIB, STMDA, and STMDB. So it means that the associated addressing modes adds up to the instruction giving the names like this. So as we discussed in the last class, how we are using an instruction LDMIA R0 colon, I mean not, R0 with not symbol represents an update. So it is like pre-increment with the write back. That's the meaning. So and the address and the registers addressed are R1 to R3. So it means we have load store multiple instruction increment after, load store multiple instruction increment before, okay. So likewise you just decrement after, decrement before, you list like that. So STM increment after, STM increment before, STM decrement after, STM decrement before. So you are going to decrement the memory first and then put the value. So increment the memory and then put the value. So accordingly you need to understand. So in this example, what is that? LDMIA R0 is there, R1 to R3. R0 was having the address 80,010. It was earlier pointing to 80,010. So when we do LDMIA, it means 1, 2, 3 will be loaded respectively. 1, 2, 3 will be loaded respectively. That is what's shown here. And your R0 is updated. R0 is updated to the address 80,001C. That is what shown here. The next time what happens if we say what is that, LDM instead of IA, IB, LDM, IB, if you say, then what will happen? Increment before, then store the value. Then you just observe increment before when you do, so it will store the value instead of 1 2 3, it will store 432, 432. Likewise, we have listed in the last class, you just cross check that value 432, that value I have shown, that is LDMIB. So with that respect, so what are all the important aspects which we have seen are, just let me take the page. So what are the important things which we have seen, which to be understood clearly are is nothing but trying to making use of STMIA. Okay, I should be clear with this. Sorry. Then STMIB, then STMDA. So decrement after STMDB. Try to use these instructions. So that is for storing. Similarly, how you did for what is that? LDM. This example we have seen. What is that? LDMIA we have seen first. What is that? Load, store, multiple instruction, increment after. So it means get the register value and store accordingly, and increment after. First increment and then store. That is called increment before. So you just see what is that? Store the value and then increment after. Here now store increment before and then store the value. You can say like this. So what is that? LDMIB. That is what the example we have seen. So for every instruction, you can write those blocks called as graphical representation showing the memory location and thinking what is that, whether I need to increment the memory to the register or not, where it is pointing before moving or after moving. So that is what the simple understanding of these instructions. That's it. So LDMIB. Then what is the left out? LDMDA, decrement after, then LDMDB. So that's the picture. Now you just see, if I wanted to, if you use a store with the base update, then the paired load instruction of some number of registers will reload the data and restore the base address. How to do this? It means the concept of restoring. I mean, I have stored some data to the registers. Now let's suppose those register values have been changed. Then if those register values have been changed, how to restore back? So that is what, in such situations, any combination of these things will work. Let us take an example. What I'm trying to say is how these multiple instructions which I have listed are useful. So the people can ask something like this. For example, if I wanted to have something like this, what is that? Preconditions. I'll just write down first. Let's say R0 is having 0x 9000, let's say. Okay, so if this is the value, then R1 has what value? So let's say R1 is equal to 0x some value. Let's say R1 is having some value, let's say 9. R2 is having some value, let's say so 8. Okay, then let's assume R3 is having some value. What is that? 0x, let's say 7. Okay, so if we have these values, now let's assume if I use the instruction like this. What is that? STMIB. What is that? store multiple instruction and increment before. Okay, so what is that? The base register is R0. Okay, I'll put a not signal to ensure that update. Okay, after execution of the instruction, R0 will be updated. That's the meaning of that not symbol, right? What is that? R1 dash R1 dash R3 I will write. It means that R1 to R3 register I am considering. Now let's understand what is that we are doing now. This instruction says that some values we are storing in the uh, registers. Let's assume registers. So it means what values we are storing in the registers. So if we say move R1 comma 0x, let's say instead of that directly I can pass the value hash 1. Let's say I'm passing the value 1 to R1. Okay, so now move R2 hash 2. Okay, so let's say hash 2 move R3. So it means I'm just passing the forceable value, immediate value with the move instruction, which is a simple data transfer instruction, which moves the value 3. Okay, or even if you want to represent in terms of numbers 0, 1, 0, 2, 0, 3, we can pass, let's assume. So now if we check now, what is that? In before giving post of this, one more pre I will perform. What is that pre? Let's say R0 is equal to 0x 9000, okay, 900C, and then I'll say R1 is equal to 0x 4 zeros, okay, it's the value. Then I'll say R2 is equal to 0x 0002, some value I passed. So let's have the difference. Just try to understand what is that. If I give R3 is equal to 0x 4 zeros followed by 3 zeros, let's say 3. So 1, 2, 3 values I passed. Okay, then I'll say what will happen. LDMDA I'll say, and I'll say R0, and I say R0 and not, it means you update after execution, and the value is nothing but R1 to R3. So that's the indication. Now you tell me, if I write here, what is this? Post. What will happen for the post? So when you execute both the instructions, so first you observe in the precondition, R0 is there, R1, R2, R3 are moved with the values 9, 8 and 7. These are the values. So R0 is pointing to the address 9000. Now STIMB R0, comma R1, R2, R3. So when you do that, so the register get updated with these 7, 8, 9, let's say. So move R1 comma R2 comma R3, when I say 1, 2, 3, so you are passing, okay. So what is that? STIMB instruction stores the value 7, 8, 9 to memory. That's it. So it means it stores the values 7, 8, 9. What is the indication of this instruction? Let me say in a simple words. Stores the values of R1 to R3 to the memory location. 7, 8, 9 to the memory. We then corrupt these values. Corrupt these values how? by moving R1 with 01, R2 with 02, R3 with 03. It means R1, R2, R3 values I changed forcibly. I wanted to restore the values. So load reloads the original values and restores the base pointer. This, which one? LDMDA reloads the original values, okay, and restores the R0, R1. So it means when I do R1, R2, R3 as this thing, R1, R2, R3 are having 1, 2, 3. 1, 2, 3 as values. But now I want them back like this. What is that? R0 should be 9000. R1, R2 should be 987. So that is what happens with the instruction, he says. What is the result which will come? See here, very important point here. First condition, STIMP says that these register values are moved to the memory. Which register values? R1 to R3. What is R1 to R3? 987. And what is the base address? 9000. After that, base address gets updated. What is the value it gets updated? 9000C. Please understand, 9000 to 9000C. Now when it gets updated, that is R0. That, and also I change the values R1 to R3 by using move instructions. With move instruction, I passed 1, 2, 3. When I passed 1, 2, 3, R0 was pointing to 9000C. R1, R2, R3 are having the value 1, 2, 3 now. So if you execute LDMDA R0, okay, the registers associated as R1 to R3, it means that I am reloading the registers R1 to R3 pointed by the address R0. Okay, so it means the values which are stored, which are nothing but 987, are reloaded to R1 to R3. So after executing both the preconditions, what we will get back is R0 is equal to 0x 9000 back. That's the simple meaning. So R1 is equal to, only thing is in exam some replacement in the addresses and utilization of mixed instruction of SI STMIA with LDMDA can be used, or STMDA with LDMIA can be combination can be asked. So any combination if you work out, you can easily think out how you are updating the register values and the memory values. That is the simple meaning over here. So what is the R1, what the value it gets updated is nothing but it restores the value which is 9. Again same thing. So after execution, that is post, we'll have the value 8, and then we have the value for R3. Okay, R3 is equal to 0x0007. Okay, that is the value. So this is the result. So we can have like this. It means changing the contents of the memory location with the values from the register. Even the register get disturbed by some other instructions like move instruction, we can retain those register values back, calling back from the memory using load multiple instruction. We can store to the memory using store multiple instruction. Okay, so just get in that way. Just a minute. Okay, so now you just understand one more thing. Okay, so if we illustrate the use of load store multiple instruction with a block memory copy, which is very important. If I wanted to do a block memory copy. How to do that? So I wanted to use the load store instruction by to perform block memory copy. Copy the blocks of memory. I mean the content. So how do you do this? The simple routine which we'll discuss copies the blocks of 32 bytes. One example we'll see which is having 32 bytes. Please understand 32 bytes. So 32 bytes means you can say uh, byte is 8. So I can name it as 8 words. 8 words. You can call it as 8 words. How you will copy the 8 words which are stored in the consecutive memory locations from source locations to destination location. Please understand. Move from, what is the task involved? How do you move these set of values, that is block, okay, from source to memory, from source location to memory location. So how do you do that? So the simple set of instructions which forms the program, you can call it as, what is that? Let's see. If we are saying, what is this? One instruction I'll use. What is that? LDMIA. LDMIA R9. I'll use R9 not, okay, comma R0 to R1. Sorry, R0 to R7. If you say like this, total 8. So total 8 registers. So 8 words it can handle. That means 32 bytes. Each one can handle one word. Okay, one word of 32 bits. So now store 32 bytes. Now first, what is that? Load 32 bytes from source and update R9 register. This is what it is called, right? What it does? Low LDMIA does write one line. That becomes easy. What is that? You can write it as comment line load. I'm writing like load 32 bytes, or in bracket if you want you write it as 8 words. Each word is of 32 bits. 8 words, right? Load 32 bytes from where? From source. From source. Source is where R9 is pointing. Where R9 is pointing is called a source address of the memory. Source and update. Update the R9. Update the R9 pointer, you can call it as. Update the R9 pointer. So it means just one instruction I wrote. Now if I write STMIA, okay, STMIA, I'll use the register R10, R10 not, okay. Here I'll write the same values like R0 dash R7, R0 dash R7. So in this, what I will do, I'll call this as store, okay. So what is this? I'll call it as store what you will store the same words. What is that? 32 bytes, which is nothing but 8 words. 32 bytes, which is nothing but 8 words, okay, 8 words to destination. You just think of now, you are storing 32 bytes to the destination memory location, okay, and you are updating the R10 register. R10 register. So what will happen, you can visualize. So next what we will do, so once you update, okay, Once we update, let's write, I'll compare now. You just check now. What I'll compare? R9 with R11. Just try to understand. R9 is pointing to one address and R11 is pointing to some other address. If R9 and R11 are 0, when it is compared, it is 0. Okay, branch if it is not equal to 0. Okay, branch if it is not equal to 0. Loop. So it means that I will go somewhere. It means I'll put it under loop. Okay, so it means we are in a loop. Let's say above, I'll just declare two things. What is that? What is this R9? It is pointing to the memory location we said. Which memory location? Let's say I'll name it as points to the start of the source data, source memory location. Some memory I'll reserve. I'll call it a source memory location where source data is present. Start of the source data. Okay, R9 is pointing there. If I take R10, R10 is pointing to start of the destination. So destination, start of the destination date. So similarly, R11, if you take R11, it points to very interesting point, end of the source. So it means R11 is present, it is pointing to the end of the source. That we should remember. So it means that I need to define R9 as the starting address, okay, and R9 as the starting address, and what is that I'll do? R10 as the destination, R11 as the end of the source address. So you can show here with the diagram, let's say a simple block diagram if you draw. So if I take like this, so you can see here in this, you can see here, this is the one block I will show. This is another block I'll show inside this. You treat these as memory locations. Okay. So now I will say the first memory location, this one, as the source. The entire box is, big box is the memory location. In that, one who starts with 8,000, another who starts with 9,000. 9,000, I'll take some set of memory location as source memory location, and another set of memory location as destination memory location. So when I write here destination, okay, so the meaning is you are pointing source locations, these many destinations equal to source, we can say, or here there is no such bifurcation. We are naming accordingly a block of source memory locations, a block of destination memory location. Now we'll take a register pointer. So we'll point to the first memory location, first point. Okay. So what is this? This is the end, because from bottom we are listing. So you just say now, I will say this one is one more. This is the point where I started. So I will name now. What is that? This one I'll call it as R9. I'll call it as R9, and I can call this as R11. That's how you should understand. So what is the size of the source? R9 to R11. R9 is pointing, let's assume 8,000, 80,000, let's say. R11 may be pointing to 80,000, 15 or 20, some set of memory location. R11 is pointing to end of the source memory location. R9 is pointing to the start of the source location. And whereas the destination now, is the R10. It is pointing to R10. So this is the destination where it is pointing to R10. So that is the structure we should write, R10. So like this. So think of like this. Now what we are doing, we are copying the block of data from source to destination. This is the block. See here, very simple 4 instructions putting under loop. You can say what is that? LDMIA R9 is utilized, LDMIA R9 is utilized, STMIA R10 is utilized. It means R9 is pointing to the start of the source, R10 is pointing to the start of the destination. That's it. And the end of the source is required. That's what R11. It means R11 requirement comes only when R9 gets updated till it reaches R11, and all the values will be continuously passed. R10 will be updated till it reaches the end of the destination. So R9 and R10 are updating themselves to reach to a certain value. Now here in this case, in the source, R9 has to reach up to R11. The same set of locations will be R10 is also reaching. So that is what the update means here, that not symbol means. So after execution, it points to the last memory location which has been moved or which has been received, you can call. Okay. So when the comparison is done, it means here the values. The source is having, let's say, R0 to R7. R0 to R7, it means they are pointing to these addresses. All the values are passed to destination addresses, that is R0 to R7. So loading the register values onto the memory location, okay, and storing onto the memory location. So with the help of registers only. So from the memory location to the register, from the register to the other memory location. So registers are used as intermediate things here. Now comparison is R9 and R11 is done because R9 has reached, after passing all the values to the destination, R9 has reached R11. So R9 will definitely be equal to R11. If the comparison is says equal, then it comes out of the loop. Otherwise, it repeats until R9 becomes equal to R11. So this simple loop program will copy the block of memory from source to destination. You should understand clearly because any kind of values are used here in the registers. You need to specify R0 to R7 means 8 registers. It means 8 words. Each register can handle one word of 32-bit, you can say. So 32-bit, 8 words means 32 bytes. So a question might also be asked, I wanted to move a block of memory which is of 64 bytes. I wanted to move a block of memory which is of 48 bytes. So any kind of question can be posed. So in such situation, you should be careful with specifying the registers R0 to R7, not only R0 to R7. If, for example, 64 bytes I mentioned means R0 to R15, that's how the number of registers. So you just have to think over in that direction. You need to write the registers. But if that is the case, then you need to limit the number of registers in LDMA. That's what they will also be specific about, saying whether 32 bytes or 16 bytes or 48 bytes maximum, I hope. Because interrupts, when they come across, they can't wait till the LDMIA and STMIA has to execute, but they have to wait. That is the disadvantage of this load store multiple instruction. That's what the compiler will restrict LDMIA and STMIA to a lower group of registers. That's what they have taken here, R0 to R7. What is the maximum? That is the limit that they will specify. So this is how you are using passing the memory location from R0 to R9 in the same way. You can think over. This is a simple example, but very interesting example which has to be understood. Now let's say if this is the block transfer, what is the next instruction which is left? Okay, So the next instruction left, what we need to study is your what is that called as simple stack operation. Okay, so just give me a minute. Yeah, what comes next is your stack operation. So which is again the continuation. So next operations what we are going to discuss, a stack operation, or you can call it as swap instruction, or what you can call it as the uh, software interrupt instructions. Will also make use of these instructions only, like store multiple instruction along with increment after, increment before, likewise. But slight changes with the instruction leads to some other name, which we call it as the other operations, like stack operation. You can see here what is the slight change we can observe here. So let's say if I call stack operation, what are the changes which we can observe here? Okay, so ARM uses the load store multiple instructions to carry out the stack operation. So what is that? Load store multiple instructions. Load store multiple instructions are used for stack operations. For stack operations. For stack operations. Okay, so that's the simple meaning of it. How? What do you mean by stack operations? So stack operations are nothing but pop operation. Okay, one is called as pop operation, another is called as push operation. This you already know, pop operation and push operation. Okay, so what is this pop operation? So removing the data from a stack, removing a data from a stack, removing the data from a stack. Okay, then placing the data onto the stack, placing the data onto a stack, removing the data from a stack, placing the data onto a stack, respectively called as push operation and pop operation. Pop means popping the things from the stack. Push means pushing the things onto the stack. Here things are nothing but your data. So stack is another set of memory location. You can call it as stack is, okay, stack is a special memory location. You can call it as memory locations itself. You can call it memory locations. They are also memory locations reserved for stack operations only, reserved for stack operations. Okay, So now what happens when using the stack, you have to decide whether the stack will grow or down, grow up or down in memory. You need to understand whether the stack will grow up or grow down. Okay, grow up or grow down. You need to decide accordingly. Okay, so it means that if the stack is either ascending or descending. So meaning is whether sorry whether it is ascending or descending. That's the meaning. So simple way to understand ascending or descending. So now one important point, I said whether it is growing, it means ascending, correct? Whether it is growing down means descending. So A and D are the words which are regularly used. Ascending stack grows towards higher memory addresses. So it means when I say it as ascending stack, ascending stack, when I call it as ascending stack, what it happens? It grows, okay? It grows upwards, correct? So when I say ascending stack, stack grows towards higher memory addresses. Stack grows towards higher memory addresses. Please understand, higher memory addresses. When we say descending stack, so stack grows towards, can say towards, grows towards lower. Words are very important. That's what lower memory addresses. Okay, stack goes towards lower memory addresses. So it means that when you use a full stack, the stack pointer is the term which comes, which is a register, right? Stack pointer points to an address that is last used or full location. That is, SP points to the last item on the stack. Okay, in contrast, if you use an empty stack, stack points to, stack pointer points to an address that is first unused or empty location. Okay, so last location, if it points, that is full stack, it means that is called as full stack. So it means SP points to last location, we can call it as last location. Last location mean to say it is last full location. It means the stack is full and the last memory location is pointed by SP. Whereas empty stack means it means stack pointer is pointing to first location, first empty location. Okay, it is pointing to the, how to write that, first empty location, you can call it as first empty location or first unused location, you can call it as. So three words we understood by this. What is that? One is the stack operations, we make use of load store multiple instructions, pop operation and push operation, popping something from the stack onto the register or pushing something from the register onto the memory. So that is push operation, pop operation and push operation. So stack will be having growing stack either upwards or going stack downwards. If it is upward, we can refer it as ascending. If it is downwards, we can refer it as descending. Ascending stack means it grows upwards towards higher memory location. Descending stack means it grows towards lower memory location. It means towards start of the location, you can call it as. Full stack, when we say stack is full, or full stack when we say SP is pointing to the last location. When we say stack is empty, the stack pointer is pointing to the first memory location. These are the minimum understanding and requirement with respect to stack operations. Now, which are all the instructions which are available? So it means we have load and store instruction. We have load and store instruction for which I need to attach them. So when I say pop means removing data from the stack. So it means removing data from the stack means stack is a memory location. Removing the data from the stack means taking the data from the stack and moving to the register. Who does the job of moving contents from memory to the register? We know load. So load M remains same. So for this, I will attach what is called as addressing mode. You can refer it as FA. What is FA? Full ascending. Okay, full ascending means stack is full and it is ascending, you can call it as. It is going to higher order memory location. Please understand. So I can have LDM FD, full stack descending or full descending. You can call it as full ascending and full descending. Similarly, I can write what is that? LDM EA, empty ascending. Please remember, I said in the above, full stack means full. Full ascending I attached. Full ascending, stack is full and it is growing towards. Stack is full, it is going downwards. It means full ascending means I am there. The location stack pointer is pointing to the top of the stack, you can say. Ascending mode it is. Descending mode means I am coming down, but still I am at the top of the stack. LDM means load, multiple instruction. EA means empty ascending. Empty ascending means top of the stack, stack pointer is pointing to the first empty location or first unused location. Okay, so similarly, I can have LDM ED. LDM ED means empty and what is that called? Descending. Empty ascending, empty descending. So if all these I can name them as pop instructions. So all these I can name them as pop instructions, okay, for the stack. How about push? If I want to push the data, push the data means pushing the data onto the memory. How do you push the data onto the memory? So the same thing, STMFA I'll use. Okay, I can use STMFA. Then I'll say STMFD. Correct? STMFD with the full stack ascending and full stack descending. So if you write now STM EA like this, so then I can say it as STM ED. So these are the pop and push instructions respectively. Okay, where they are pointing, you need to be very much careful in understanding where the stack pointer is pointing. Based on that, the naming is given, whether it is a full stack or empty stack. Based on that, respectively, for the pop operation and the push operation, the respective instructions can be used. For example, if you take let's take up onto this. Okay. So let us take, what is that? If I write like this, you try to understand the stack operation, which is similar to what we discussed till now. Let's say if I write R1 is the register. So it has the value, let's say 2. Okay. So a 32-bit value I need to write. So I have written it as R1. Then R4 I'll use. Let's say register R4. So what is the value I'm using? Is 03. I'll just type 03. 2 and 3 I stored in the registers R1 and R4. Now what is the special register we are using? Stack pointer. What is the stack pointer is pointing to? Let's say it's a register. It has the value in it 0x 000. It has 8014, something like this, 80,014. So this is the address where stack pointer is pointing. Now if I use an instruction, sorry, if I use an instruction, what is the instruction I'll use? If I use an instruction stm, okay, what is that? Store multiple instruction. I'll use fd. So it means full stack decrement or descending. Full stack descending. It means stack is full, stack pointer is pointing. Now we need to go in descending order. It means I'll use the instruction sp not. So it means I need to execute the instruction and update the SP register where it is pointing to. That's the meaning, right? We already know that. So if I write now R1, okay, comma R4. So it means only two registers I am referring to. That's what the comma is used. Okay. Now if you see this, what happens? You are pushing onto the full descending stack. Pushing onto the full descending stack, you can see that when a stack grows, the stack pointer points to the last full entry in the stack. Last full entry in the stack. Okay. So what will happen? So if we just understand this, now I'll just simply write, if I write post, what is the post result? R1 value, I'll write R1 value 0x, okay, 0x00, how many zeros? 7 zeros, okay, 2. R4 will have 3, just try to understand. R4 will have 3 again, 0x 000 3. And then SP now, you just observe, SP now will point to 0x 000 80,000 C. Why it is so? How it is happened? So the simple idea is it basically goes like this. So it means what is the address earlier I was having is 000. I'll just write down the address so that it becomes easy. What is that? 0x. Directly we'll write the address instead of all zeros. Let's assume this as the address. Okay. So what is this? This is the address. Now 0x 8014. I mean 80,014. Okay. So let's say 0x 80,010. So you can have the gap of what is how many locations you can see there. 0x 80,000 C. So there is a each one with a particular range. You can see that. Now what is the value present here if you cross check in this particular address? Okay, before execution of the instruction. Before execution of the instruction, we are showing the memory location how it is. So what it was telling is 0x18 was having the value according to the program. So it was having the value 2. So this was having the value, sorry, 1. It was having the value 1 and this was having the value 2. This 2. Then you can observe here, this is empty. This one is empty. Okay. So when you just execute, where now you can observe that here it is pointing, it has gone. Okay. So you can see that, please cross check the textbook. You can see that the stack pointer is pointing to 8014. After execution, now the stack pointer will point to 8000C. So that is what the 8000C updated and the stack is full. So 1, 2, 3, 2. Those values are updated to the stack. So that is what updating the stack, emptying the stack are done using STMFD, STMED. So just try to have a look into that so that completes the stack operations, simple stack operations. Even you can do the stack operations in a rigorous way, how you can check the stack overflow, stack underflow by cross verifying, subtracting the stack with the stack pointer with the size, comparing the stack pointer with some registers. So one or two instruction using LDMIA instruction I can use to make sure that how a simple stack location can also be built. So you cross check. Okay, simple one or two examples. If you solve it, that is the stack pointer. So some swap instruction is a simple one. Then program register instruction, if we just do it along with interrupts, that completes this instruction part. I'll stop here. We'll do the remaining things in the next class. So tomorrow, since we have MTech exam, I'll not be